Hello everyone, in this video we will cover the section 3.2. In this section we will continue to study second order linear differential equations. The general form is written here, you see. The coefficients are functions of the independent variable t with initial conditions y of t0 is equal to y0. The value of the derivative of the solution at the same point is equal to y1. So here we will answer some questions for this differential equation. The question one is that in which condition do we have exactly one solution for this differential equation? What is the condition to say that we have exactly one solution of the second order linear differential equation? So this is answered by the theorem written here. Consider the initial value problem, namely the second order linear differential equation with the initial conditions written here, where P, Q, and G are continuous on an open interval I. Then there is exactly one solution which is a function of t of this problem, and the solution exists throughout the interval. Namely, in order to say that we have a solution, exactly one solution for the differential equation written here, the coefficient functions have to be continuous on an open interval I. Okay, so we emphasize that the theorem says three things. The initial value problem has a solution. In other words, a solution exists because of this theorem. The initial value problem written here has only one solution, that is, the solution is unique, and the solution is defined throughout the interval I, where the coefficients are continuous and is at least twice differentiable there. Okay. For example, find the longest interval in which the solution of this initial value problem is certain to exist. In which interval do we have exactly one solution for this differential equation? When we look at carefully the differential equation, so we see that it is linear second order differential equation, because when we write this differential equation in the form written here, namely the coefficient of the second derivative should be 1. So to get 1 for the coefficient of the second derivative, we will divide this equation, this equality by t squared minus 3 times t. Therefore, we obtain the second derivative plus, so this one is actually written as t times t minus 3, and in the numerator we have another t. So by removing t, we get 1 over t minus 3 y prime plus t plus 3 over t times t minus 3 y is equal to 0. Okay. Also, this is an homogeneous differential equation because the right hand side of this equation is 0. Okay, g of t is equal to 0. So here we find that p of t is the coefficient of y prime, which is equal to 1 over t minus 3. You see, 1 over t minus 3, p of t 1 over t minus 3, and q of t is the coefficient of y, which is equal to minus t plus 3 over t times t minus 3, and g of t is equal to 0. This is a constant function. The only points of discontinuity of the coefficients are t is equal to 0 and t is equal to 3. At t is equal to 3, p of t is discontinuous, and also q of t is discontinuous, and also we have another discontinuity point for q of t this is t is equal to 0 because of the denominator. Okay, g of t is continuous everywhere. It is a constant function. Therefore, we have 2 points that make discontinuous the functions. Therefore, we have 3 possibilities for determining an interval such that the coefficient functions are continuous. Since we have 2 points, 0 and 3, so we can write from minus infinity to 0, from 0 to 3, and from 3 to plus infinity. Okay. So when we look at the initial condition, so the initial value is 1 for the parameter t. Therefore, 1 is included in the second one from 0 to 3. Therefore, the longest interval such that we have exactly one solution for the given initial value problem is the open interval from 0 to 3. This is the longest interval in which theorem guarantees that the solution exists. Okay, we will find the discontinuity points for the coefficient functions, and then we will take the interval that includes the initial value of the parameter t according to the theorem written here. The second question is that what is the form of the most general solution of homogeneous differential equation? Okay, namely, when we write 0 for g of t, we obtain homogeneous second order linear differential equation. The second derivative plus p of t y prime plus q of t y is equal to 0. We have homogeneous second order linear differential equation. Actually, we know we can find the most general solution of this differential equation by using the superposition principle. If we have 2 solutions of this differential equation, so the linear combination of these solutions, namely c1 times y1 plus c2 times y2, is also a solution for any values of the constants c1 and c2. Okay, namely, we say that we can generate more solutions by forming linear combinations of y1 and y2, which means that we have actually infinitely many possibilities for the solution of this differential equation by writing any values for c1 and c2 if we don't have any initial condition for this differential equation. So we define a determinant W. This is called the Wronskian determinant, or simply the Wronskian of the solutions y1 and y2. If you know 2 solutions for this homogeneous differential equation, so we generate a determinant written here. The entries of this determinant are y1 and its derivative for the first column, and for the second column we have y2 and its derivative, and the determinant will be y1 times the derivative of y2 minus y1 prime times y2. Okay, for example, we found that the functions written here are solutions of the differential equation, if you remember the previous section. So find the Wronskian of y1 and y2. According to the definition, we will write the entries of the determinant. The first row are formed by y1 and y2. Namely, we write directly the functions written here. Exponential minus 2t, exponential minus 3t, and the derivatives of them will be written in the second row. The derivative of the first one is minus 2 times exponential minus 2t, and the derivative of this one is equal to this one. So when we compute the determinant, you can find easily, namely we will multiply first them, and minus we will multiply them, and we obtain minus e to the power minus 5 times t. So why do we try to learn the Wronskian of the solutions? We will answer this question in this theorem. Another example, find the Wronskian if the Wronskian of f and g is t squared times e to the power t, and we know f of t, it is equal to t. So let's find g of t. Okay, according to the definition of the Wronskian, so we know its result, which is t squared times e to the power t, and the first row are formed by the given functions. The first one is t, and we don't know the second function, g of t, and the second row is found by finding the derivatives of the first row. The derivative of first one is 1, the derivative of second one is written as g prime of t, and the determinant will be t times g prime minus g, and it is equal to t squared times e to the power t. And if we write y for g of t to simplify the expression of this equation, t squared times e to the power t will be equal to t times y prime minus y, and from here we obtain by dividing this equation by t, y prime minus 1 over ty is equal to t times e to the power t. Okay, so it is linear first order differential equation. So by using the method of integrating factor is minus 1 over t, and namely the integrating factor is equal to e to the power integral of the coefficient of y, namely e to the power integral of 1 minus 1 over t dt. So from here we obtain e to the power minus ln t, and writing minus to the power of t, we get e to the power ln t to the power minus 1, and from here we obtain t to the power minus 1. So multiplying this equation by integrating factor, we obtain actually 1 over t y prime minus 1 over t squared y is equal to e to the power t. Okay, and when we look at carefully the left hand side of this equation, so we obtain it is actually the derivative of the multiplication of 1 over t times 1 over t and y. Therefore the left hand side can be written as d over dt 1 over t times y is equal to e to the power t, and from here by taking the integral of both sides of this equation, so we obtain 1 over t times y is equal to e to the power t plus constant, and from here y is equal to t times e to the power t plus c times t. Okay, so the theorem says if y1 and y2 are two solutions of the differential equation, which is second order linear homogeneous differential equation, if you know two solutions of this differential equation, and if there is a point t0 where the Wronskian of the solutions is non-zero, then the family of solutions written here, namely the linear combination of these solutions with arbitrary coefficients, includes every solution of this differential equation. Namely, the linear combination of these special solutions will give a general form for all solutions of this differential homogeneous second order equation. Okay, this theorem says that the general solution is arbitrary linear combinations of y1 and y2. If you know the initial condition for this differential equation, also we can find the values of c1 and c2. Okay, namely to find a general solution for second order linear homogeneous differential equation. The condition is that the Wronskian of these special solutions at some point should be non-zero. Okay, non-zero. For example, show that the functions y1 and y2 form a fundamental set of solutions of this differential equation. First, we should understand whether it is homogeneous second order linear differential equation to use this theorem to say that the functions given here form a fundamental set of solutions. So from here we obtain the second derivative plus 3t over 2t squared y prime minus 1 over 2t squared y is equal to 0. So from here we understand that it is homogeneous second order and linear differential equation because we have the coefficient functions and the right hand side is equal to 0, and it is in the form of linear differential equation. Therefore we can use this theorem to verify that the given functions written here form a fundamental set of solutions. So we can verify by direct substitution that y1 and y2 are solutions of the differential equation, namely to understand whether y1 is a solution for this differential equation. So we find the second derivative and first derivative of this function and we put them into the equation, and if we get 0 for the left hand side, so that means y1 is a solution. So the second derivative will be this one. Okay, you can compute easily for y1, and the first derivative is equal to 1 over 2 times t to the power minus 1 over 2 minus y, which is equal to t to the power 1 over 2, and after the computation we obtain this is equal to 0, which means it satisfies the differential equation. Therefore y1 is a solution. Similarly, the first derivative is equal to minus t to the power minus 2, and the second derivative from here becomes 2 times t to the power minus 3. Writing these values into the differential equation, and after the computation we obtain it is equal to 0, the left hand side. So the second function is also a solution for this differential equation. Next we calculate the Wronskian of them. We know y1 it is t to the power 1 over 2, y2 is t to the power minus 1, and the derivatives are written in the second row, you see, and the determinant of this 2 by 2 matrix will be minus 3 over 2 times t to the power minus 3 over 2. So the Wronskian is not equal to 0 for every positive value of t. Therefore we conclude that y1 and y2 form a fundamental set of solutions. The Wronskian is not equal to 0 for every positive value. Therefore we conclude that y1 and y2 form a fundamental set of solutions. Another example, verify that y1 is equal to x and y2 is equal to x times e to the power x are solutions of this differential equation for positive values. Do they form a fundamental set of solutions? So similarly we will find the first and second derivative of the first function. They are equal to 1 and 0 respectively, you see. Writing them into the equation, so we obtain x squared times 0 minus the coefficient times the first derivative, which is equal to 1, x plus 2 times y1 is equal to x. And after the computation, namely the left hand side will be 0. Therefore y1 is a solution for this differential equation. Similarly, the first and second derivative are written here for y2, and writing these values into the differential equation. So similarly we obtain 0 for the left hand side. So we say y2 is also a solution for this differential equation, and it is linear second order homogeneous differential equation. And then we will find the Wronskian of these solutions, x times e to the power x. The derivatives are written here. We find the derivative of the second one by using the product rule, and then the determinant of this 2 by 2 matrix will be x squared times e to the power x. It is not equal to 0 for every positive value, you see. Therefore we say that they form a fundamental set of solutions. Okay, using the theorem we can find the general form of any second order linear homogeneous differential equation. Thank you very much.